Hello physics students, Mr. Standerson here, and in this short lesson we're going to talk about work and power. So please have some notes ready, jot down any questions that you might have, and you can ask me later at always. So the first thing we're going to look at is what work is in a scientific sense. Remember that work is done when there is a net force applied to an object and the object moves in the same direction as the applied force. So that direction piece is pretty key when we're taking a look at how the forces help us understand if work is done or not. They must be pointed in the same direction. Or a component of the force, if it's at an angle, must be in the same direction as the distance moved. All right, so we'll come back to those ideas, but remember that is our definition for work. How we calculate work mathematically is using this equation. Work is equal to force times distance, where the W stands for work, F is force, and little d is distance. The unit for work is a joule. Force is measured in newtons and distance is measured in meters. So we'll always come back to those SI units. So when we're taking a look at a problem, like maybe there's a child in a chair and lifted out of the chair, there is a amount of force that's applied to the child to lift that child up, and they're going to move a certain distance. If we know those two quantities, we can calculate work, and we will just look at that equation. Work is force times distance, plugging those numbers in. And the work in this case is equal to 250 newtons of force times 0.75 meters. So we get an answer of about 333.3 repeating joules of work. Okay, and we're going to be coming back to those kind of ideas. So make sure you can substitute in, rearrange, and solve. All right, so conceptually, remember we went back to this idea of the force applied, that net force has to be in the same direction as the distance traveled. All right, so that's going to be a really key thing when we talk about our forces and how they are help us define if work is done or not. So in this case, if we draw a really quick free body diagram, there's a weight force of the tray and there's an upwards applied force from the waiter. Okay, now if he's traveling, he might travel a distance that is horizontal. So he might go from here all the way to here. The force and the distance in this case are not going to be in the same direction. Therefore, there is no work being done in this example. So those are some ways to think about if work is done or not. So let's take a look at a couple examples here. So let's say we have James, and he studies for 4 hours for a test. Now that is our common definition of work. It is not work being done in a scientific sense. So I'm going to cross that out. A water rocket launches off the ground. There's a force, and force is applied in the direction of motion, causing acceleration. So yes, work is done here. So we have work happening. A weightlifter holding, here's a key thing, they're holding 150 pounds over their head. That is not work. No work done there. There is no distance move. Alex pushes a book up a ramp. Yes, that is definitely some work. We're changing the position, and we're applying a force in the direction of the motion. All right. Again, a bigger one, but it's too heavy and it doesn't move. This would be no, even though that's the box on the ramp, there is no distance traveled, so there would be no work. All right, so we'll cross that one off. Box sliding down the ramp. This would be yes, and it's actually work in a negative direction for this case because it's decreasing the amount of mechanical energy. All right, so we're coming to a lower spot, decreasing that energy. And then a mother holding a baby for 30 minutes. Nope, no work there, no distance. And the father lifting a baby up from the floor. This would be yes. And it would be positive work because it's increasing the amount of mechanical energy. All right, so those are some things to kind of think about as we're trying to decide if it's work or not. Okay, so coming back, how do we know if a force is doing work or causing an energy to change? Think about if the net force is causing that acceleration, then it is responsible for changing the energy of that object. All right, so let's say, for example, we take a look at a baseball, and right before contact, there are some forces acting on it. There's a force of gravity, and then, of course, we also have the applied force from the bat. All right, so we have this force here, force from the bat. okay? But only one of these forces is really going to be responsible for changing any energy, and that would be the force from the bat. The gravitational force is not going to be a factor in this because it's not in the same direction. So the work being done by the gravitational force is not factored in when we're going to take a look at these kinds of scenarios. All right, so why is that important? Well, when we can help us answer some questions like this. So what happens to the energy as work is done, right? So if we have a book that slows to a stop as it slides across the floor, work is being done on the book, but we have to identify what force is doing it. All right, now this is true. There was originally a person pushing on the book, but that's not the part of the free body diagram once it's sliding to a stop. So the inertia keeps us going, not a person pushing on it. We know that from our previous chapters. The force of gravity is also pulling down on the book, but is that really what's causing it to stop? I would say no. Frictional force, however, is acting on the book, and it's going to be doing work. It is changing. It's the one that is causing the acceleration. There is an upwards force, the normal force, but that's still not causing any accelerations. So this would be the one to pick, and as a result, the mechanical energy is decreasing. It's going to change from a high amount of mechanical energy to a lower one when it comes to a stop. All right, so take a look at this scenario. Same kind of idea. Baseball is being caught and brought to a stop upon hitting the catcher's mitt. The work done on the ball. These other forces do exist, but ask yourself always, what force is causing the acceleration? And in this case, it would be the force of the catcher's mitt pushing against the ball, and it again decreases the mechanical energy of the ball. All right. Last example with this, if a child is pushed in a swing and the swing is set in motion, the work done on the child by the father is which one of these examples? Is it the seat of the swing? That is a force, but in this case, not the gravitational force is not doing the work, and the swing holding it in place is not doing the work. It's really only the force applied by the dad and the child that's doing the work, and this one would increase the mechanical energy. They would gain more potential and kinetic energy. All right, so that's a big thing to think about, the force that's causing that acceleration. Another thing we're going to take a look at is power. Power is the rate that work is done. So when we think about it, is how much work we can do in a given amount of time. All right. The equation is the power is equal to the work divided by time. We'll use capital P for power. Remember, W is work and little t is time. The unit for power is a watt. And you could just capitalize that by capital W. I know it gets confusing with work, but look to see if it's a unit or a quantity. And then, of course, we have our work, which is measured in joules, and our time is in seconds. So these are the units that we're going to be coming back to in order to identify power. Now, conceptually, power can be kind of thought of in this case. If we have two students, Will and Ben, and they're in the weightlifting room, if one student, Will, lifts a 100-pound barbell over his head 10 times in 1 minute, and Ben lifts it 100 pounds over his head 10 times in 10 seconds, which student does more work? Well, if you think about it, it's kind of a trick question because they're both lifting the same amount of weight, the same distance. So it's the same force if they are the same height, right? But one of them is doing it much faster, okay? So if they are the same height, then they are doing the same amount of work, but the student with the most power is the one that can do it in a faster amount of time. So in this case, Ben would be the most powerful because it is doing it in less time. Okay, so we're going to come back to some of these big ideas, but for now, remember for power, it's in watts, and many appliances use watts to kind of think through for you to kind of compare their amount of energy usage. And energy is something that is going to be related to this idea of work and power. We're going to come back to those ideas in a little bit. Like I said, make sure you have these in your notes, and if you have any questions, please reach out.